Ngalakin Khadijan Nyunga Boja.
Hi, welcome to today's module, and we'll now start a new chapter, chapter 2, where we will look at, I'm looking at my course reader here, continuous time, LTI systems, and the Laplace transform. Now, this is a fairly long chapter. I've actually merged two chapters from my previous notes, and I'm going to cover continuous linear time invariant systems. And please be sure you've actually gone through the module regarding chapter 1. All the chapter 1 modules where we actually introduce what we meant by linear time invariant system. And we'll carry out some analysis of how you work out the response of these systems and the properties of these systems to be able to be sure that we can design and operate them. We'll do this firstly by looking at the basic concepts in the time domain, which we can understand and see what's happening, but the mathematics and the techniques become a bit brittle and cumbersome, unwieldy. And then we'll go to the so-called Laplace transform, which although it becomes a bit more abstract in something called the S domain, the techniques become a lot more simpler. And as engineers, we will suffer whatever mathematics gives us as long as it simplifies the analysis and design. For most of us, we just use the technique and we may forget where the technique came from, how it was developed. And in some cases, perhaps that's a good idea. And if you have completed the unit in maths where the Laplace transform was covered, you probably see it's a fairly complex transform, but it yields very simple processes for analysis and design. But before we look at the Laplace transform, let's start off with the basic ideas of what is a system. Let's now get me to share my screen. This time I'll share. For this, I'll actually share my whole screen so I can jump between the lecture notes and OneNote. Oops, and I don't want to share that. I'll go away. Okay. Problem with sharing screen is you get other things popping up in the way. So these are the chapter 2 notes. Let's go to the start. That's where it is. And what we need to do is define what a system is. A linear time invariant system mathematically. That's the key point. Now, in the notes, we start off with the definition of the system as linear differential systems, where X is an input to a system and Y is the output to a system. If you went through the chapter 1 modules, you will realize that's how we define systems. X is the input, Y is the output. And the way we model a system, the T that we use in chapter 1, is, for this case, as a set of ordinary differential equations for both the output and the input. Now, we shouldn't accept these equations unless we are convinced that these actually represent the systems that we will be using as engineers. Since most of you will be electrical engineering students, the basic system, the basic linear time invariant system you would see would be what you would have seen in your first year circuits. Systems consisting of resistors, capacitors, inductors, and excited by voltage sources, current sources. These are the inputs. And where you measure things like voltages and currents, these would be your outputs. So the best way to appreciate this, if you haven't had a chance to do that already, is let's look at the very simple circuit. So I'll jump ahead to the first example, and then I'll go back and generalize what we have just done. So for this example here, let me activate my annotation sharing tool so you can spotlight tool. That's it. So you have a simple RC circuit. You can use node to datum analysis or nodal analysis if you want to work out the voltage across the capacitor, which is, by the way, our output Y. So our output Y is the voltage across the capacitor. Our input is, not surprisingly, or not unsurprisingly, or unsurprisingly, the voltage. It's the input. So that being the case, applying nodal analysis, this is what you get. And you need to, well, you need to set it up in a form that you can solve it for. So what we do is we rearrange it in this form, where we have the x on the right-hand side, the inputs on the right-hand side, and the outputs on the left-hand side. So if you see here, you have that goes to the right-hand side, and these two, this component and that remains on the left-hand side. Now you'll notice I've introduced the D notation. Now the D notation is, and this is where I can jump to my OneNote, is defined as this. A very clever way to simplify the maths. In other words, rather than using this notation here for differentiation, replace it just by D. And it allows us to do a very clever trick, as we will see right now. Oops, wrong one, not there yet. And it allows us to literally extract the D outside the Y. So here, this would be, here this one would actually be D, Y, T, and the D is treated as an, I'm not sure if you can see my pointer. Okay, the D is extracted out as we do here, and we can do that. We can actually do that. So we cleverly rewrite it in this form here, and effectively have Y here, X there, and that is some sort of polynomial in D. If we wanted to change our output as the loop current, in other words, instead of having this is the output, this becomes the output, we can use mesh analysis. Oops, mesh analysis to give us that equation. And similarly, the denotations allows us to convert an integral to a 1 over D expression. So we can actually write it like that. And it allows us to do some simple calculus as an algebraic operation and convert it to this differential only equation. We do not like to see integral equations. We want to convert everything to differential equations. So this motivates our idea that we can describe any such system, no matter how complicated, as this. Linear differential equation of Y on the left-hand side and X on the right-hand side. And if you use the D operator, we convert it to effectively two polynomials, one representing the Y and one representing the X. A few things to note. M has to be less than or equal to N. That means that the highest power of the input is always going to be less than or equal to the highest power of the output. And in fact, as we will see, we usually have the highest power of the X less than the highest power of the output Y. There are various reasons for that. The main reason here is that if that doesn't hold, the system will technically not be stable. In other words, if you remember our definition of stability, bounded input, bounded output, that will not be the case if M is greater than N. And there's various ways you can show that. And I'll leave it to you to explore that from the recommended reading texts, or if you want to Google. But effectively, stability and also noise will not get amplified. Noise also will make the system possibly unstable. Okay, now we can skip over this example. Once we have our definition, what do we do with it? Well, the reason why we provided a mathematical definition of a system is we want to work out the response. If we're given the input X, and we're given the system as a differential equation description, can we work out the response Y? In other words, can we solve for Y the differential equation? Yes, we can, but it's not a simple step. And there are various ways you can do this, and this is one way that you may have learned in your maths. And I don't have access to your maths notes, so decided to use good old Google and came up with this math exchange question, which was, the question originally was, what is the difference between homogeneous and particular? Do you remember homogeneous particular solutions in your maths? If you covered solution of ordinary differential equations in a maths course, this is how you will do it. you will refer to the homogeneous and particular solutions, two types of solutions. This math exchange answer is actually pretty much spot on. And this is probably how you would have solved for differential equations in your maths using a homogeneous and particular solution. But in engineering, we're more interested in the modeling and, if you like, the modeling aspect and the physical model aspect of it, and how we use it to design, analyze systems. In maths, it's more of a conceptual basis. And in fact, the second solution here pretty much covers it when there's a discussion of linear subspaces and null spaces and kernels, very mathematical, very fundamental. So if you are doing advanced maths or do maths units, you probably appreciate this more than most other people. But for us engineers, it doesn't help us. We take the maths that helps us in the analysis and design. And in this case, homogeneous and particular doesn't help as much as what we will call not homogeneous particular solutions, but responses, and two types of responses. Zero input, which is not unlike, and in fact, I think it's actually the same as the homogeneous solution, and the zero state response, which is in fact a bit different to the particular solution. So they're not completely the same. But the way these have been defined is in the context of a system which has an input, has an output, and we also define a new concept of a system. It's got a state. Now that's something new. We didn't discuss that in chapter 1, that the system has a state. So a zero input response is the response when there's no input, zero input, correct? That makes sense. And the response, okay, well, first of all, if there's no input, how do you have an output? Good question. Normally, if nothing goes in, you would expect nothing to come out, and that is strictly correct. However, the system may have an internal state, and that state will generate an output. So the zero input response is in fact how the state of the system allows it to generate an output. But what do we mean by the state? Let's go back to our example. Do you know from your circuits that you can have an initial charge over a capacitor? That is a state. It's the energy on the capacitor. So for circuits, your state comprises of energy, voltage across the capacitor from the energy storage, and initial currents through the inductor from the magnetic field effect. These actually represent the state of the system. Now, obviously, to charge up the capacitor and to run a current through an inductor, you would have applied an input. But maybe you remove that input. What happens to the system? So you apply an input to the system, charge up a capacitor, run current through inductor, pull away the input. In a sense, that is what the zero input response sort of gives you. It gives you what happens when you've reached the system has reached the state and then it has no input. That is a zero input response. However, the way we've defined it is that in addition to a zero input response, you now apply an input or a different input. We usually assume that the state is there. We don't try to work out where the state comes from. Although in practice, the state must have been generated by something that was input to the circuit or to the system. But then what happens is maybe we have changed the input. And if you've done a unit in circuits, that's exactly how you would normally do this. But for our mathematical abstraction, we simplify and say at time t equals 0, the system has a state, and we use 0 to identify the epoch. And if it's got no input and it's got a state, we would look at the zero input response. But to work out how it responds to an input, we then work out the response solely due to the input. In other words, the zero state response. The input is active, but the state is set to 0. So your capacitors have no voltage, the inductors have no current. The only response you get is purely to do with the input. You can see, if you think about it, that the two together is the complete response of the system to an input and to an initial state. And that's how we model systems. We define t equals 0 as the epoch where an input is applied, or more often than not, the input gets changed, or the input gets changed, and also the time where you have a state of the system that you need to use to work out what happens to the system irrespective of the input, the zero input response. Now, the zero input response will usually decay with time. So that's an important behavior, because if you have no input and you have current energy in the system, the energy has to dissipate, so the response will tend to decay. So the zero input will not last long. The zero state response, however, will last as long as you have input. So if you keep applying an input, you'll keep having a zero state response. So in the end, when you take any system and analyze its response, it's more than likely what you're seeing is that, because the zero input response will have disappeared by the time you may get to measuring it. Of course, if you change the input, then you will get an effect related to the zero input response. And that's something that we probably won't be looking at in this unit, but you will see when you do more advanced circuits and you apply these types of ideas. Let us now get on and see how we look and solve for the zero input response. So we have our equation, polynomial in D. How do we solve for this? It's a bit unusual. In other words, what is the y for which all this differential is equal to 0? And the reason why this is 0, of course, is there's no input. So this side all becomes 0. You'll notice that if x is equal to 0, all its derivatives will also not exist. So the right-hand side is strictly all zeros. There's no x at all. So you're left with the left-hand side. Well, the only solution that you can have, apparently, is an exponential solution. The exponential solution is what you might call how all these systems behave. They behave in an exponential manner because that's the only way that you can have all these derivatives go to 0. And you can see that because of this important property that the exponential function has, which is its derivative. The derivative of an exponential function is another exponential function. So it allows you to pull that exponential function out, and you're left with here a polynomial equation for which you can solve its roots. It becomes an algebraic problem. Now this equation here is known as a characteristic equation. It's characteristic because it characterizes the system and the behavior of the system not due to an input, because this side here is equal to 0. It will have n solutions, n roots. For us, solving it is a mathematics problem, and we'll go through we'll go through some parts of that, but we're more interested not so much in the solution, but the form of the solution. Because for us engineers, we like to know the type of signals that we will get. So if you have real distinct roots, you will get exactly what we set up, what we said we were going to get, an exponential. But you'll have n exponentials because you have n roots. You have a linear combination of them. Also, this is a constant because this will always solve that equation no matter what value of c. This will always solve that equation no matter what value of c2. So you effectively have an infinite number of possible solutions. This is the general form. What is the specific solution? You must have a specific response, right? How do you work out C1, C2, and Cn? You will need to know the state of the system. I did say you have a state. That state has to be quantified. And the state is quantified by deriving so-called initial conditions for which you'll need to find n. And the way it's set up is you will find n. If your system generates an nth order differential equation, it will actually have n different state conditions that you can actually extract. What does the response look like? It's going to look like that, an exponential function. Now, which of these responses are the ones that you should really be seeing? This is what you should see. As I said, the zero input response is supposed to decay with time. This goes up. If you get a response where sigma is, where this thing, I think sigma, where this lambda is positive, something's gone wrong, because that will imply that the energy increases with no input. That's contrary to all the laws of physics. So you can't just get any arbitrary mathematical differential equation, it's got to be quite a specific form to follow the physical circuit. So this shouldn't happen. This is also not possible. You can have that, but let me put it this way: you can have if you use your ideal circuits, you can get that. In practical circuits, you'll never get that. I'll leave it at that discussion. What you should get is that there. And the reason why this goes down is because of any lossy elements in your circuit, any resistances. The resistances are the ones that cause this to go down. Now, when I was saying this can go straight, it can if you have no resistances, but all circuits have some resistance. You cannot have R equals 0. If you set your resistance element to R equals 0, that means you're ignoring all the other resistances that you probably don't usually model because it's just so small. So this can never really happen, not in a real circuit for which you will have some resistance in the circuit. The other possibility is that these are mathematical possibilities. When you solve for the roots, you'll actually have repeated roots. If you do that, mathematics tells us this is the solution that you get, and what you end up is you create this new form, which goes like that. Now, real repeated roots, I don't know, to me they're like quite unique. It's like you just happen to have a circuit with the right value of your resistors, capacitors, inductors that just happen to give you two roots which are the same, exactly the same. Not that likely. Can happen. I don't see it happening that often unless you deliberately set out to design a circuit with that behavior. You're more likely to get this situation or the next one. Complex roots, yes. When you solve second order equations or anything above second order, you can get complex roots. Remember this guy? Where is it? Got too many things here. That's the one. Remember the quadratic formula? That can give you complex roots. Now, here's the fun fact. Because our differential equation has real coefficients, the roots occur in complex conjugate pairs. Complex conjugate, asterisk. Remember we discussed that? The importance of the complex conjugate? Here's the real reason, or one of the real reasons why. Because when you solve these real equations with real coefficients, you always have complex roots which occur in these pairs, where if you have an alpha plus j beta, you must have an alpha minus j beta. So you need to describe this as a complex conjugate. Wow, that's actually quite important to realize. And there's a good reason why, because the form of the solution is this, which means strictly speaking, your output is complex valued. Real input in, real valued circuit, complex output? Not really. In fact, this is not complex. If you go through and simplify, this is what you get. Of course, you can only get this real form if you have complex conjugate pairs. Voila, that's it. That's how it works. What's interesting is, what does this look like? Yes, you get an oscillatory zero input, which you hope will decay. So this should usually be a decaying form, and it oscillates. So when you have complex roots, the zero input doesn't just go down like that, it oscillates. Maybe now's a good time to go through some examples, now that you're probably getting a headache, wondering how the heck do I unpack all this that we've learned. So we'll go through these three examples and then describe how we're doing this. Now, this is just the maths, so we don't worry about how we got this. If you have a circuit, we need to get this from doing some form of a mesh or nodal analysis, and this is what we get, as we did in the example. Now, we also need initial conditions. I only mentioned them, but I didn't say too much about what they are. To solve the differential equation the way we have, carry this out in this style, we need to know things about the y. That's the only way you can do that. So the first thing we need to know is the value of y at 0. That's the first. The initial conditions have to happen at 0. So to define for time equals 0. After all, for time beyond 0, this is what we're trying to solve for. We don't know but we should know the state. The state is defined as the what we can measure about the system at time t equals 0. So we have to measure what happens at the output, 0. But that's not enough. We'll need, in this case, since this is 2, we need 2 initial conditions. The second and subsequent ones are all the derivatives of the output, from the first to the second to the third and so on. So we need to look at the derivative of the output and the first order derivative of the output and figure out what that is. And for this particular circuit that we've made up, the first derivative of the output gives you -5. How you get that from your circuit is not entirely straightforward, and we will have one example where we show how we use the nodal and mesh equations to actually get the initial condition that we need. And A, B, and C, the only difference between these three is the form of the differential equation and, of course, the initial conditions that we use. So let's solve. So this is the characteristic equation, lambda squared, 3 lambda plus 2 equals 0. Solve for the roots. What you get, real distinct roots. General solution, you don't need to look it up, you just remember it. Lambda plus 1, the root is -1, so you get e to the minus t. That's lambda plus 2 is -2, the root is -2, so it's e to the minus 2t. And you throw in these two unknown constants that you have to solve for using the initial conditions, C1 and C2. Now you also need the first order derivative of y, of the output. So this is what we do here. So we need to take the derivative of that. That gives us this. And then we equate these to the initial conditions at t equals 0. So at t equals 0, when t equals 0, this should equal C1 plus C2, right? Because e to the 0 is 1, well, that's e to the 0 as well, that's 1. C1 plus C2, and that is equal to the initial condition 0. One equation. Second equation, we look at the derivative, t equal to 0. That will give us -C1. That will give us -2C2 when t is equal to 0. That is equal to -5. Second equation, we solve as we normally solve simultaneous equations. For C1 and C2, C1 is -5, C2 is 5. This is the actual solution, and we plug it back in, and that is the specific solution. We can now plot that because we know the particular values that you have here. Also, this solution only exists for t greater than 0. Remember that. That's important. This does not exist for negative time because negative time we're not looking at. Sometimes in the test and exam, in the tutorials, we could have it in this form here. Let me put my drawing tool. The form could be this. We have used the unit step. Remember what the unit step was? The unit step here, the UT, to tell us that this only exists for positive time because UT is equal to 0. In other words, there's no output at t less than 0. And of course, if you like, you can also do this. Okay, so that's another form that you may see the solutions in the tutorial solutions and other textbooks. They should either have it like that, or they can have it in that form there. Okay, now I'll wipe this out. I need to wipe this out because this is on my screen. So when I scroll the page, this will be made stuck here in place which is not very helpful. So away you go. Okay, let's look at the next one. Now, you're probably not shocked to see that we're deliberately trying to look at the different types of solutions. So this is one where you have repeat roots. The form of the repeat root, if you have one repeat root, is this form here. And I'll jump through the notes just to show you that. Okay, I should have stopped the recording. It makes it easy for my others. You see me scanning up and down too quickly. You can get a headache, and I get a headache. So this is for real repeated roots. If you only have one repeat root, that would mean this. We actually have this case here where R is equal to, assume R of the n roots are real, but okay, you have two roots which are the same. I think that's the right definition. So in that case, you would have C1 plus C2T. Now it's R would be 2. Yeah. So this definition means you can't have R equals 1. If you have repeat roots, you either have 2 roots which repeat, 3 roots which repeat, 4 roots which repeat. You can't really have 1 root which repeats. By definition, it would not repeat it. It would not repeat. So R equals 2 is the smallest number you have. So the simplest expression is C1 plus C2T times that, which is what we have. So that's the solution. Now, once again, we also need the derivative. Remember, we need both the output at t and also it's the expression for the output at t plus its derivative for the initial conditions. This now is getting a bit complicated. Well, not that much, but this form here requires you to use the product rule. So, the algebra is going to get a bit more tedious, and it's already starting here. So that's what you get there. Now you look at the value of t equals 0 for this one, t equals 0 for that one. When t is equal to 0 here, the good news is you're only left with C1. When t is equal to 0 here, this one also disappears, and you're left with negative 3C1 plus C2. The 3 and the negative 7 are, of course, the initial conditions. We have to go back and see what they are. It's these guys here. So 3 and 7. We solve, once again, in fact, this one's even easy to solve because of this, and we end up with that as our solution. Great. Now we get to the last one. No surprises, you're going to get a complex solution, and of course, it's going to occur in complex conjugate pairs. So you get 2 roots for a second order system. This is the 2 roots. They're in complex conjugate pairs because this is J6, this is minus J6. The real part is the same. We know it'll be of this form here. If you go back through the previous pages, where the alpha is the real part, so that becomes negative 2, and the beta is the imaginary part, so that is 6. That is the form. Now, this is where the algebra does get tedious. You need to work what this is for t equals 0. That's easy to do. Just set that t equal to 0, t equal to 0. And that's equal to the first initial condition. Then you look at the derivative and set that to the second initial condition, 16.78, which means you got to take the derivative of that. Okay. Also need to use the product rule. Gets a bit complicated, but still doable. And then you get 2 equations. And then you realize, oh, these are nonlinear equations because of the cause. So solving it is not as straightforward as what we did here or previously. They're not your standard simultaneous linear equations. They're simultaneous nonlinear equations, thanks to the cause. So solving them can be quite tedious. And if you go to the recommended reading, one of the textbooks, where they actually solve it for a complex case, I was surprised that it is a bit of a job to actually get to it. This is where you just say, oh, thank goodness we have computers to do all this. And thank goodness our lecturer is not going to give us in a test or exam anything like a complex number. And that is true. In fact, I think I did run one exam where I did give out complex roots, but I had to actually provide how to solve it. In other words, I want it to waste of time, but if you've got tools to do this, this is the stage where you say, just go to your Mathematica or MATLAB or programmer or calculator and just get it to work, to give you the roots and solve for this. And that's really what you do. You don't really want to do this on paper. You can do real distinct roots on paper, and that's what you'll probably be tested on. Maybe repeat roots, but really you don't want to look at this just because of the tedious algebra. What's important here for us is that you're going to get a decaying exponential. So in a sense, the form of the response is as important as the specific response. After all, we already know what the response is. This is just detail, the fact that this is a 4 and a negative pi on 3. It takes a lot of time, 2 pages worth maybe of derivation just to get that detail. But we already know what we're going to expect. It's going to be a decaying exponential. And sometimes that's probably all you really want to know, depending what the problem is. Now, something about the initial conditions. And this is where I want to finish off. This is getting a bit long. This presentation is getting to be a bit long just because I went through the trouble of describing things to you. So please feel free to skip ahead and to jump ahead. But if you want to get the full picture, then you really have to go through all of this discussion. Now, this is a bit, I'm not going to read this out. What I will read is this part. We denote t equals 0 minus as the instant just before t equals 0. And similarly, t equals 0 plus as the instant after. The reason is t equals 0 is important. That's the time when the initial conditions exist, and that's the time when the input is applied. 0 minus is before the input is applied. 0 plus is after the input is applied, which means there is a change. There's a step change between no input, some input. And that's why we differentiate just before 0 and just after 0. What happens at 0, in fact, we don't know. So strictly speaking, we should never use 0. We should use either 0 minus or 0 plus. What we've done here is perhaps for the purists incorrect, but what we really mean here is 0 minus. In other words, it's the initial condition before we apply the input. Because once we apply the input, the system will change. So if you like, the initial conditions are those that exist at t equals 0 minus, just before you apply the input. Let's finish off with this example. This is an example that will carry through late to other modules because we want to get to work out a total response for this second order circuit: inductor, resistor, capacitor. So this has everything, and it's written in such a way as understandable to people who analyze circuits. You have a voltage, and it's described by this, and you notice the voltage is the unit step. So it indicates that the voltage is applied at t equals 0. Before t equals 0, there was no voltage. T equals 0 is the epoch, and this is the form of the input. We want to work out the loop current. That is our output, yt. We have initial conditions on the actual elements. So the initial current through the inductor is 0. So since the current through the inductor is the output current, is the same as the output current, which is through the loop, then we can say that. And you notice we're using 0 minus. It's before the input is applied. The initial capacitor voltage is 5. That is also before the input is applied. There we use the value Vc because it's the capacitor voltage. You probably recall that we wanted initial conditions to be in terms of Y. We're not given that. We're given what we know about the capacitor and what we know about the inductor, because that's what we know about the system. So as I said, there's going to be a bit more background work before we get to what we just did now, a couple of minutes ago, solving it. The background work is the circuits analysis. So first of all, KVL around the mesh. I'm going to use the D notation just to keep things simple. Can you see that that's the differential equation that you get? And that's an integral, by the way. That's the voltage. That is the inductor. That is the resistor. That is the capacitor. Now, that is the voltage across the capacitor. So it pays maybe at this stage to immediately rewrite this as VCT. In this case, it may be helpful to write it that way. Depends what you want to do. You have to keep it in this form because you want to retain only the inputs and the outputs, or you keep it in this form because you can associate it with a number like this plus 5, for example. So let's do that. Let's replace it by VC, and let's look at what happens at 0 minus before you apply the input. So this is what you get. Now, before you apply the input, that means this is 0. Also, we know we know that the initial condition of the current is 0. So that's 0, that's 0. That is 5. Ooh, can you see what this is going to tell us? That is 0, that is 0, that is 5, and I need to draw this. Let's highlight this. And go. We have our second initial condition in the right form. So we had to convert a voltage through the equation to the initial condition we need to have to solve it. Okay. That's important to remember. So we have the two initial conditions. Now we can get the characteristic equation from that. So the characteristic equation comes from this one. So once you take this, you need to multiply through by d. And you need to move the x to the right-hand side, so you get that. And then from that, you can extract the characteristic equation. That's what we have. These are the roots, plus 1, plus 2. Hey, it's the same one we had before. We actually saw this before, the same equation coming up. And in that case, with these initial conditions, and we have the same answer. So the same equation, but I think it's a different circuit, although we get the same equation. Actually, let me go back. Okay. I just confused myself. So we didn't have any circuit. We just stated it. Here we go. That's the one. So we've actually done this back to front. We've actually solved the problem. We probably solved it before we were actually given what the problem was. Not good engineering, is it? This is halfway through it. This is the first part is how you get to this, and I've given you, and here's the example that we've used. This one here. This circuit gets us to that with these initial conditions. That one, these initial conditions here, using this circuit, and that's the response. Now to finish off this module. This is just to highlight what we mean by the 0 minus and 0 plus concept. So I'll read this through and highlight. Just before you switch on the input, the total response, now this is the total response, what the circuit actually does, is of course that the output current is 0, because we said there's no current through the inductor, the input has not been applied, so obviously it's 0. We also saw that the voltage across the capacitor was 5, and from that we derived this. So that is also true before we applied the input. But at t equals 0 plus, the input becomes active. Now, we know from circuits that even though the input may switch, the voltage across the capacitor cannot instantaneously change, and the current through the inductor cannot instantaneously change. So we can't say this. In other words, even though the input switched on, the current is still 0, and the voltage across the capacitor at least remains at 5. However, the input does jump from 0 to 10, because at t equals 0, that becomes 10. So when we go back to this equation here and replace the 0 minus with 0 plus, which is what we have here, and plug in the values where this now is 10, this now is the same, which is 0 as it was before. This also is the same, which is 5. Because this is 10, this becomes plus 5. Compare that with that. So you see what's happened. The initial condition, one of the initial conditions at least, has changed from -5 to 5. And that's because the moment you apply the input, the system will change. The state of the system is automatically going to evolve. And what's evolved is the derivative of the current, which effectively means the voltage across the capacitor, actually the voltage across, the voltage across the capacitor doesn't change, the current through the inductor doesn't change. So what must change is the voltage across these guys. And that will change the derivative of the current from -5 to +5. Okay, that's all we need to cover regarding the zero input response. And yes, I did spend a bit of time, and I'm sorry it's a bit long, but I wanted to really cover everything. Students, usually when you go through it, you have all these questions. And if I did this in a formal lecture, I just skip through and say, you can work it out yourself. Guess what? I've helped you work it out. I've actually gone through and showed you the various components and where they come from. So when you see these problems, you should be in a better position to understand what you need to do. Now, we've only solved half the problem. The second half of the problem is a zero state response. And before we can even consider how we do the zero state response, we got to finally bite the bullet and talk about the convolution integral. But no, not this time around. I have a special module that follows this one where we discuss everything you need to know about the convolution integral. Watch out for that one. And thank you for today's presentation and attending.